relationship between humans and groundwater. So we've seen this map before where there are aquifers underlying different parts of Tennessee. Many of them are carbonates. So here's a carbonate aquifer, and this is all carbonate aquifer. And some of them are sandstone or other sands. But that means that these are the places that we are drawing groundwater from if we are using well water. And in a lot of places, we at least use well water, and that might be diverted to municipal water eventually. But a lot of the water that we use ends up ultimately sourced from these aquifers. So we need to understand something about how we are interacting with the groundwater to know cases when we might accidentally pollute the groundwater or use too much of the groundwater, etc. During wet times, the water table is going to be high. So we talked about the water table fluctuates with the amount of precipitation. And regardless of how deep your well is, you can probably pump water out of it to get water into your home. But during droughts, the water table drops so much that shallow wells might run dry because they no longer intersect with the water table. And that can even be exacerbated by the fact that pumping of water, if you pump enough of it, it does lower the water table around. Drought thus can affect the level of the water table enough that some wells can run dry. Even though we think the drought is going on Earth's surface, it affects the groundwater too. When you pump water out of a well, so you have to put some energy into it, some sort of a pumping system that draws that water up. You're pulling water that would be in the ground out. And that creates what we call a cone of depression, which is a cone of area where that water table is depressed, is lowered relative to where it normally would be. So all that water that you've pumped out came from this area here. And as you pump out more and more, that cone of depression can widen and start to affect the water table further away from you. That means that heavy pumping of particularly deep wells can create a cone of depression that actually drives nearby shallow wells to become totally dry. So if you drill a deep enough well and you pump enough water out, you may cause your neighbors to actually run out of water. Overpumping in general, it lowers the water table. Because, as we saw, surface water is connected to groundwater, you can actually end up draining rivers and swamps nearby if you overpump enough for large industries or agriculture. It can cause something called saline intrusion, where salt water from the ocean, if you lower the water table enough, salt water can intrude in instead, and it can spoil your wells essentially permanently, because now all the water that you're drawing in is salt water. It can also, overpumping that is, can also collapse pore spaces and rocks. As you remove the water that's supporting those pore spaces, they can collapse, and it causes land subsidence or sinking. Land subsidence due to removal of groundwater, well, land subsidence in general is what has caused, we think, the Leaning Tower of Pisa to lean over time, because the pore spaces under that corner of the tower have collapsed. This diagram over here shows a point in the San Joaquin Valley where the ground surface was actually marked at different points in time, and that land has subsided because so much groundwater has been pumped out. So the ground surface actually used to be way up here, right, 30 feet above his head. And then 30 years later, it had lowered to here, and then just 20 years later, it had lowered again. So over time, the San Joaquin Valley has actually subsided by a substantial amount. And that is all due to groundwater removal, pumping out to support all of the plants and all of the agriculture that we do in this area, even though it's a semi-arid environment normally. Let's talk about saltwater intrusion. So there is groundwater under the ocean, and a lot of it is salty. And the balance between where the salt and the fresh water, that margin is determined by the balance between recharge and discharge in the aquifer itself. So if you pump enough water out, you can start to draw in salt water. And if you pump too much, then that salt water starts to intersect with your well, and you will start pumping out salty water. So this is really a problem near the coast, near the oceans already, but if you pump out enough water, you can end up getting salty water. Sometimes your very deep aquifers, even away from the ocean, are salty. And in those cases, you have to be careful not to drill your well into a salty aquifer, because then all you're going to get out is salt water. The Florida Everglades are a system of swamps in southern Florida that has a very unique ecosystem. And because there's been so much development in southern Florida, we are starting to destroy the Everglades purely by removing the groundwater that is supporting those swamps. Because we're pumping out water, we're actually draining those swamps because, remember, that water table where it intersects with the surface is going to be where you have surface water. So because you're pumping out groundwater in other places, you lower that water table and you reduce the size of the Everglades. Let me talk briefly about something with particular importance to us in Tennessee, that is karst. And karst refers to a land surface consisting of many depressions called sinkholes. And that is because the rock in those areas easily dissolves. And as a result, you can get a system of caves developing. And on Earth's surface, if those caves collapse, you get sinkholes. So karst is related to the fact that some rocks dissolve easily, especially limestone. And so in eastern Tennessee, we've got a lot of limestone. We have karst because that limestone can dissolve fairly easily. Because that limestone can dissolve underground, you can generate a system of caves, some of which are just, partially filled with water or fully filled with water at depth or partially air filled. Regardless, if those caves are near Earth's surface, that means that there's not a lot of rock supporting the ground surface above them. And at times, they can collapse. So you can see new sinkholes or evidence of old sinkholes as small depressions on the surface. And often those are not filled with water because the water just percolates straight downward. And it's easy for it to enter the cave and then it flows very quickly because these are kind of like giant pore spaces that the water can flow through very easily. If you, in a karst landscape, you'll have other things like disappearing streams. And so the stream might flow across Earth's surface and then disappear underground where it enters one of those caves. And it will only exit where the ultimate surface, the water table surface, intersects with the ground surface elsewhere. Why is it that limestone dissolves so easily? So limestone is made of calcite. And if you add just a little bit of acid to that calcite, you can dissolve that carbonate and produce dissolved calcium, water, and carbon dioxide. So your rock turns to dissolved solids, water, and a gas. And that's because the acid reacts very easily with carbonates. So that same acid reaction that causes chemical weathering like this is what produces karst terrain. And karst occurs naturally, it happens naturally because rainwater is naturally acidic. It's slightly lower in pH than neutral. And so over time, that slightly acidic rainwater can eat away at limestone. Karst terrain slowly forms as that acid dissolves that limestone. And it might dissolve more in some layers than others. And over time, you can develop a whole set of sinkholes in a particular spot, such that if you were looking at a topo map, say, you'd see a bunch of those circles with hatcher lines on them, indicating that they're closed depressions. Oftentimes, they won't be filled with water. Here's just a quick example of what one of those dissolved limestone caves can look like, right? All of this space that you see used to be filled with rock, but acidic water over time has dissolved that rock, made this space, and then some other water percolating downward through groundwater has come up through these cracks and precipitated some new minerals there. And so that's why you see this set of speleothems, which is the general name for stalactites and stalagmites. So the stalactites holding tight onto the ceiling are just there because groundwater percolating through precipitates some minerals as it enters these caves. We can overlay this map of caves on the map of the groundwater, and so, or excuse me, the type of aquifers that there are. And so this area over here was a sandstone aquifer. We don't see very many caves in that Cumberland Plateau. This area over here is an unconsolidated sand aquifer for the most part. But then these two areas here where you see all of these caves, these are areas where the aquifer and many of the rocks near Earth's surface is limestone. As a result, you get a lot of caves forming in those spots. Wherever you have limestone aquifers, you're going to have a lot of caves, and you're probably going to have karsty landscape. Here's a picture of what one of those sinkholes can actually look like. So unbeknownst to the people that were building the city, there was a cave developing underneath them. And over time, the surface got broken away enough, eroded, weathered and eroded away enough, and there was enough new construction on top pushing down on it that eventually the roof of that cave gave way and you collapse into a sinkhole. Here's another picture of a sinkhole where you can see a similar thing has happened. And any of the buildings that were around here just collapse right into the sinkhole when it occurs. And they can occur fairly suddenly. We can guard against them by doing seismic tests to identify places where there are caves close to the surface, but it's not always a perfect solution. Here are some pictures of what results from the karsty landscape that we have in Tennessee. So I see these a lot if you look at cattle fields, just because you're not going to build on places that are really at risk of karst. So what's good to put there? Well, foraging grounds are pretty good. You know, cattle feedlots are good to have in those spots. And you can see lots of little depressions in the land surface here. And a lot of those fields, and those are there because these are old sinkholes. You'll oftentimes have sinkholes open up near people's houses, and that can be pretty scary because then you don't know, is the sinkhole right underneath my house? And now they're going to need a seismic survey out here to make sure that their home is still safe to live in. And it also results in many caves around eastern Tennessee and parts of central Tennessee as well. We look at this map, we can see a map of where the most sensitivity to karst is. So green is some sensitivity, yellow is moderate, and then red is the most sensitivity to karst. And so if we look at Knox County here, we see that the entire thing is sensitive to karst. And so depending on where you are in Knox County, you might have some sinkholes forming below you. Let's move on to a slightly different topic and talk about groundwater pollution. So we can talk about how groundwater moves with the pollution, how the pollution itself actually moves alongside the flow of the groundwater. And an important thing to note is that the groundwater flow is going to carry contaminant plumes along with them. And so those plumes will migrate in whatever direction the groundwater is flowing. If your groundwater is flowing this way, then any pollution that you have from things like leaking surface tanks or underground tanks, or septic tanks, or acid mine waste from a mine, all of those are going to percolate downward until they hit the water table, and then they're going to move with the flow of groundwater. Remember that when you pump groundwater out, you can actually cause groundwater to flow towards that cone of depression. And as a result, pumped wells can actually draw pollution towards themselves. So if you pump in an area where you've got a lot of fertilizer pollution or industrial pollution, you put a well down there, you're likely to pull that pollution towards that well eventually. So here's an example where you've got some small well that has been drilled and it's picking up clean water because it's not pumping out a ton of water and because the general flow of groundwater is still away from that well. But if you put in a new well nearby and you start to heavily pump it, now instead of flowing to the left there, all of this groundwater is going to flow to the right towards the lowest groundwater. And that means that your pollution is now going to enter your small well. That is, heavy pumping can draw pollution into nearby wells. So it's not just your pumping, but the pumping of your neighbors that matters. All right, folks, thanks for listening to this short lecture on groundwater. We'll see you online.